Hello and welcome back. Integration revision for year 13s. I believe this is lecture number 9, but I could be wrong. However, we're going to go through questions 92 to 103. I finished on 91, I believe, the last time. It's a total mix. It's not necessarily going up harder and harder. There will be some very easy questions. On this particular lot, from 92 to 103, I glanced very, very quickly before I started, and there's actually very, very easy integrals to do today. So let's not waste time, and let's go with integral number 1, number 92, which is the integral of 3 on the denominator, 3x minus 2 to the power of a half dx. Okay, is that difficult to do? Absolutely not. It's very straightforward. It's a linear adjustment, really, if we write to the top. Careful, I think there is a little snag here, and I hope you don't write me things like this. You move it to the top, and this becomes now something atrocious such as this. If I was at liberty to give marks for this, I would give 0 marks. Year 13, and you think that is the same as that, is really dreadful. This is 1/3. The 3 lives at the bottom. He gets very, very angry if you move him, so please leave him at the bottom. This is 1/3. It's the bracket here that can be written on the top, of course, as x minus 2 to the power of minus a half dx. And now the brackets of the form ax plus b, linear, so it's at the higher bracket, will go to the half, and there's no change there, there's just x, so we just need to take care of this half that's going to come to the front. Is it 1/6, the third divided by half? I was only kidding. The answer is, of course, 2/3 plus c, which of course you can check with differentiation. Okay, but please use your calculator so we don't make mistakes. We got to integral number 93. Let's write it first of all. Is 6x plus 3 on the numerator, the whole thing divided by 2x dx. What can we do in there? Some kind of substitution, some kind of trig identities? I don't think so. This just actually splits, because we've got a single item on the denominator. 6x divided by 2x is, of course, 3, and then 3 over 2x, you have to be careful, 3 on the top, 2x at the bottom, dx, and now this will integrate instantly. This, of course, will integrate to 3x with respect to x, and this is plus 3 over 2, the log of the mod of x, not the mod of 2x. I have mentioned this in the past. I've done quite a bit on it, and discussed it. If you put in a UK exam 2x in there, you probably, well, almost certainly get away with it. Technically, it shouldn't really be a 2x. It's because that is, of course, 3 over 2 times 1 over x. That's this bit here. And then, of course, that's the coefficient, 3 over 2. And this, of course, should give you your log of x, and that's the end of it. Okay, number 94. 94. It's another rational expression, and we have 4x plus 1 on the top over 2x minus 5. I actually copied it wrong. It should be 4x plus 1 on the top dx. How can we integrate that? There are 3 choices. The majority of teachers for something like this, they will say do a little long division first of all, because this is improper. We got x over x, so there'll be whole bits in there, and I hope you can see the whole bits will be 2. There are some people say use a substitution. That will work with substitution. U is your denominator, so you can split it. And of course, I have shown in the past, I'm not going to do neither. I'm going to manipulate this by a little bit of juggling if you want, or dribbling, whatever analogy you want to use. So I'm going to write it as 2x minus 5, put that in a bracket to keep him warm, and then on the top I'm going to create exactly the same bracket, 2x minus 5. I think I've done a whole lecture on this where I showed how to manipulate things like that, done loads of examples. So now I need to create my top. My top is 4x plus 1. First of all, a 2 there takes care of the 4x, but now by putting a 2 there, I created a minus 10. And I need to be worth plus 1. So if I go minus 10, I need plus 11 dx. So that is exactly the same as that. How does that help me? I can split my fraction. This will give me this item divided by 2x minus 5, which will give me 2, plus 11 over 2x minus 5 dx. That integrates instantly. The 2 will integrate, of course, to 2x, and this is just a simple log. Careful, because you got that chain there. The log of mod of 2x minus 5, but you got times 2, so we need to take care of that, plus 11 over 2 log plus c. Number 95, let's make some space. It's another rational expression, something of a something. So this is number 95. I think we've done a similar one. I think I remember something which looked almost like that, if not the same. I hope it wasn't the same and I have the same question twice. That's number 95. Okay, how do we do this particular question? 1, 2, 3 different ways actually it can be done. It's very flexible, this one. It's a very nice question. Most people at first glance, they will see the difference of squares on the denominator, x squared minus 1, x plus 1, x minus 1, and then probably they will go partial fractions. Is that a sensible method? Well, I'm not going to question the sensible. I'm going to say it will work well. It's going to be perhaps a little bit tedious with the partial fractions, but it will work. Is there another method? Yes, there is another method. We can use the substitution. U is your denominator. U is x squared minus 1, and then again that will work. Is that sensible? Again, not sure if it's sensible, but it will work. But what is the best method for that? Well, when you're having rational expressions, I did say, and perhaps I didn't use it on the last one, I didn't question, is that possibly of this type, is check if your denominator differentiates to your numerator. X squared minus 1 differentiates to 2x. The 2 is not a problem, it's the x that's there that allows me to do that. So I'm going to write it as 2x on the top, dx. And I need to be worth 4x, so I'm going to stick the 2 on the outside. And why is that? Because when you have a situation where your denominator differentiates exactly to your numerator, the answer is always the log of your denominator. Let me actually write it. I've written it down enough times, but one more would not hurt. So if we have that, like we have here, then the answer is always the log of your denominator, plus c. So in this particular case, this integrates instantly. We've got a 2, which is at the front, log of mod of x squared minus 1 plus c. And that's this integral done. Substitutions, or if you do partial fractions, you will get an equivalent expression. Just in case you've done it by partial fraction, you're wondering, is that the same? You should really get 2 log x plus 1, yeah, it doesn't matter, 2x plus 1 plus a 2 log mod of x minus 1. You will get something which looks like this, and you will get, of course, exactly the same answer. Okay, number 96, yet another rational expression. What's on the bottom of this is 2x minus 1. And on the top we've got, is it 4? No, sorry, I'm copying half and half. I'm copying half from one line and half from the other. On the top of this we have x squared. I'm just checking that I haven't miscopied it. That's number 96. 96 x squared over 2x minus 1. Okay, how do we do this? This is a little bit messy. And personally, I would advise you, if you had something like this, either to do a long division or a substitution rather than a manipulation. In fact, this is the case. If I had to choose between a long division and a substitution for this, I would have gone for a substitution. Okay, how are we gonna do it here is the question. I don't want to show more than one method if I can help you today for this. Can we manipulate it? We can. We just need extra bits in there and a little bit of more work. So probably I'll do it by substitution. Play safe, because some people might get a bit confused because it's not very, very nice to manipulate. So we're going to use a substitution. U is my denominator. Immediately I will differentiate it and make dx my subject. So du by dx is 2. So my dx is going to be du over 2. And if I need more stuff, I'll come and get more stuff. So this is what I got so far. The denominator, I called it u. Nice. The x squared, let's leave him for the time being. And the dx is du over 2. And of course my objective is to change everything into u's in there. So this should be x squared over 2u du. I need to lose this x squared. I need to come here and I'm looking at this expression carefully. 2x is definitely equal to u plus 1. Do I go for x is u plus 1 over 2? I'm looking at this. The answer is probably not. I'm going to square the whole equation. So basically I'm doing this. So I'm going to get 4x squared is equal to u squared plus 2u plus 1. But of course, if I look at my integral, I don't have an x squared in there. I've got just x squared. That's not a problem. We're going to make a 4x squared on the numerator over 2u du. And in order to balance it, we're going to stick a quarter at the front. So now it's a straight swap of u squared plus 2u plus 1 on the numerator of this expression. So what are we going to get in there? We're going to get a quarter. I forgot the quarter at the front. U squared plus 2u plus 1 divided by 2u du. Leave the quarter on the outside, split your fraction. U squared divided by 2u is going to be a 2 at the bottom, and we're going to have u on the top, or if you want, a half u. 2u divided by 2u is of course 1. And then we have plus 1 over 2u du. That's 1 divided by 2u, of course. Let's leave the quarter on the outside till the very end. And let's start our integration. This, of course, I hope it doesn't confuse you. It's a half u, of course, yeah? I wrote it in a non-mathematical way, but I hope it's still okay. So I'm going to use a bracket. So this will integrate to a quarter u squared plus u, because we integrate with respect to u. And this, again, is a half times 1 over u. So that's a half log mod u plus, let's put the plus c on the outside anyway. It doesn't really matter, because even if you times it by quarter, it's just another c. So times the bracket now. So we're going to get 1/16. And let's put the u's back in at the same time. So save us just to copy and write another line right at the bottom of the board. So that's a 1/16. Our u stands for 2x minus 1 all squared plus a quarter u. And our u is 2x minus 1 with no power, plus a quarter times a half is 1/8 the log of mod of 2x minus 1 plus c. Let me just check the answer. You can actually expand it. If we manipulated this, you would have had a much simpler answer. This is what comes out of the substitution. So let me just check how I have it there. I got it as 1/16 2x minus 1 all squared plus a quarter 2x minus 1 plus an 8. This is the substitution version. If you've done it by manipulation, and you can actually simplify even from there. Just let me show you. If you square these brackets, you're going to get 4x squared. 1/16, it'll give you a quarter x squared. I'm not showing full workings here, so please, I do apologize. Minus 4x, so it's going to be minus a quarter x from this line here. And then I go plus 1/16, which I don't really care, because I'm going to shove it in the plus c at the very end. And then I got another half x from this bracket here, and another minus a quarter that I couldn't care less. It's going to go in the plus c. And of course, I've got, this does not change in any way, plus 1/8 log of 2x minus 1 plus c. And my final answer, if I did it like this, should be, and a lot simpler, of course. And I do stress you would have got this answer if you manipulated it instead of doing the substitution, it would have been a quarter x squared. Quarter and a half will give you plus quarter x. These two bits, bye-bye, they're going to go into their constant. And of course, plus 1/8 the log of mod 2x minus 1 plus c, which is much nicer, and I believe that's the answer indeed that I have up there. So this one, it was probably one of the meatiest of this particular lecture. It wasn't too bad even by substitution. I'd like to think that we are now a little bit more able with substitution. We can manipulate things a lot more fluently. If you're not as fluid as that, please use your calculator efficiently. Take your time, do the extra lines, do not rush, do not go from one line to the other by jumping a lot of steps. I might be jumping here, I've got bad habits. I'm trying to keep the lectures as well to a sensible length, otherwise they'll get too long if I show now every single step. As we're getting more advanced, I'll be showing less and less working, so keep that in mind as well, please. So number 97 is our first trigonometric integral. I did miss them actually. We haven't done one of these for a little while, so that is 97, integral of 1 plus cos to the 4 of x divided by the cos squared of x dx. Okay. What do we do with this one? Well, all trig in there. I doubt if there's any substitutions to be used in there. Bottom, does it differentiate to top? I don't think so. No partial fractions or stupid things such as, I don't know, integration by parts. So probably we need to manipulate it a little bit. What things can we do in there? Cos squared, 1 minus sine squared. Cos squared is also a half plus a half cos 2x. Different things that come to my head. Neither of them are sensible because, of course, by replacing a single item on the denominator by 2 items, I'm making things worse because it makes the fraction non-splittable. And this is the key word, non-splittable. It means how about I split straight away? Let's have a look at this. It's going to give me 1 over cos squared if I split it. 1 divided by that. And cos to the 4 divided by cos squared is just cos squared. Do I know how to integrate those two separate quantities? The answer is yes. This is a sec squared of x. Comes from the differentiation of a tan. We must know this result. We must also know, not the answer, but how we integrate cos squared and sine squared. There are identities that come from your double angle for cos. The cos squared in particular will be a half plus a half cos of 2x. This comes from the identity cos 2x is 2 cos squared x minus 1 dx. Once we're written in this form, it's practically done. I'm not even going to write anything, just to remove the bracket. The bracket there is just purely to show that this comes from the cos squared. I'm just going to throw away the bracket and integrate, because it integrates on the next line. A sec squared of x comes from a tan of x. Tan differentiates to sec squared. Done. Integrating a half with respect to x, a half x. And a cos of 2x comes from the differentiation of a sine of 2x. Sine differentiates to a plus, so it will maintain its sign into a plus. You also produce a times 2 to come to the front. So we need to divide by 2. And of course, we're going to get that plus c. And this is our answer to number 97. Okay, number 98 is one that when I looked at this list, I said, oh, I don't want to do this one. It's just very, very tedious. Not hard, just annoyingly tedious. And because I haven't done one of this particular type as lengthy as that, I have to show full workings, and that makes my life even worse. Number 98, let's have a look at it. It's a rational expression again with x's. On the top, 17 minus 5x. At the bottom, 2x plus 3 multiplying by 2 minus x all squared dx. The question is, how do we integrate that? Is it a hard integration? No. If you get an integration like this, it's actually a gift because it'll be worth a lot of marks, relatively obviously to the conceptual difficulty of the integral. You're just getting marks basically for the amount of work. This is partial fractions, but we need to remember how to do partial fractions, and that's why I said we haven't done one of these, one that has a repeated factor at the bottom. So I'm going to do the partial fractions, I beg your pardon, separately first of all for this, with full workings, because once I get the partial fractions, it just integrates instantly. There's nothing much to do. This will be identically equal to some constant over 2x plus 3. Definitely another constant over 2 minus x all squared, and possibly, that might not be there, but I have to allow for it, a constant c, which is the squared bracket but not squared, just ordinary bracket 2 minus x. I'm going to have to move this cable out of the way because I'm going to step on it one of these days. So I'm equating tops, 17 minus 5x identically equal to the a. If I'm looking at this denominator, it has the 2x plus 3, so it's missing all of that, so squared. The b, looking at the common denominator that I'm going to get, it has the 2 minus x all squared, so it's missing the 2x plus 3. And the c, I'm looking at the denominator, and in order to get to this level, it needs to take the bracket 2x plus 3, but it also needs to take one more of the brackets, 2 minus x, so it's not squared, so it needs also a 2 minus x. So for something like this now, I'm going to substitute in there suitable values for my x. In particular, let's say if x is positive 2, that will eliminate this bracket and this bracket, so all of this will be gone, all of this will be gone. And I'm going to get 17 take away 10, which is 7, is equal to 7b. So my b nicely 1. Where do I go next? The next thing to try is perhaps get rid of the other bracket. So this is now, I want to need x to be negative 3 over 2. Of course, we use a calculator for something like this. So 17 minus 5 times negative 3 over 2. I'm going to just tidy this up in a second. Anything that has 2x plus 3 is gone. So that and that is gone. And what I'm left is 2 minus 3 over 2. So if you want plus 3 over 2, all squared. What happens there? 17 plus 15 over 2 is equal to 2 plus 1.5 is 7 over 2. And if I square, it's going to go 49 quarters a. Probably the best thing to do in there is to multiply the equation, because I don't have a calculator, I'm too lazy to go and grab one. So multiply the whole equation by 4, so I'm going to get 68, 4 times 17 plus 30 is equal to 49a. That's a 98. 98 is equal to 49a, which means my a has to be equal to 2. So that the a has been done. So now we have the a and the b. We don't have the c yet, and there's no more nice numbers if you want that will eliminate brackets. Try any number you want. I like to try 0 if I haven't used it already, because it will simplify things. So if x is equal to 0, 17 take away nothing, which is simply 17. I'm putting 0 there, so 2 squared, 4a. I'm going to put my numbers afterwards, of course. That's gone with x0, so plus 3b. And if I put 0 for my x, that's gone, and that's gone. So I'm going to have a 3 times 2. Just those 2 bits there, plus, of course, a 6. Don't forget, is a c. So now I found my a and my b. So 17 is equal to 4 lots of a, which is 8, plus 3 lots of b, which is 3, plus 6c. 17 take away 11 is 6. I hope it is. And therefore C is 1. Sounds like a good number. 6 plus 8, 14, 17. Hopefully we've done it correctly. So we found our numbers. So it's best if we write the integral here. So after we've done our partial fractions, a little bit lengthy. Our A turned out to be 2. So this splits to 2 over 2x plus 3. Our B turns out to be 1. So that's going to be plus 1 over 2. I'm going to get out of the way, guys, in a second. And C was turned out to be 1. So it's going to be plus 1 over 2 minus x dx. Careful with this one because, of course, this is not a log. It's to the power of 2. So I'm advising you, rather than writing it again, perhaps wherever you got a bit of space, I'm going to write it here on the top. I'm going to write 2. That was an exam. 2 minus x to the power of minus 1. These, of course, are logs because to the power of 1, your denominator. This is not a log. So we begin our integration now. This comes from the log of 2x plus 3. It has a chain, of course, because of the times 2 in there. And 2 divided by 2 is 1, so that's rather nice. Let's do the other log as well first, and then we'll come back to that one. This is the log of 2 minus x. It has a chain because, of course, of the minus there, so it needs a minus in front to adjust it. And finally, we need to do this thing here, which is not, of course, a linear adjustment. So we're going to increase the power by 1. So it's going to go, not to the minus 1. I'm writing stupid things sometimes. It's to the power of minus 2 there. Sorry about that. Okay, so increase the power by 1, so it's going to go to the minus 1. And now we differentiate it in order to adjust the number at the front. So it's going to be minus times a minus is a plus. And of course, 1 divided by plus 1 is just plus c. And of course, you can, I probably would have written it compactly there. I put the logs together into a single log. Can I write as x minus 2 there? Will you let me? Is that okay, first of all? That's the first question to ask. It is, because of course it's a modulus there. Just checking the answer, and I'll have this answer here in my answers. Of course, you can, if you don't like 2 minus x, you can write x minus 2, but this is not modulus, of course, so you have to put the minus at the front. So this is the question done. This is the answer that I've got up there as a sensible answer for this particular question. 97 was rather long. Or actually, sorry, that was not 97. I forgot to change the number. That was 98, in fact. So we're getting very rapidly, as I promised you. This particular list of integrals is actually, I think it's only 1 or 2 that are kind of challenging. The rest are very, very straightforward. 99 is again a little bit lengthy, but straightforward. And then the next few we're going to do in 1 minute each, literally, and finish it off. That's how simple they are. So, number 99. We haven't done one of these today, so we have to do one of these as well, just for our revision. X sine of 2x minus 1. And is that it? Yeah, dx. What kind of integration is there? Product of 2 quantities, one algebraic, one trigonometric, is a standard integration by parts. So either you use your formula, use, divise, whatever how you set it up. I set it with a little cross, like a little grid, like a little sorter if you want. And if you're not sure what I'm doing, please look at one of my lectures on integration by parts. It might make more sense then, because at the moment I'm not going to be showing details. X differentiates to 1. Sine x comes from the differentiation of cos of 2x minus 1, but it also produces a minus, and it also needs a half because of the 2x. So my answer now for something like this is always equal to the product of these 2 quantities. So it's going to be minus a half x cos of 2x minus 1, always minus the integral of the product of this diagonal. So it's going to be minus a half cos of 2x minus 1 dx. I got two minuses there. Please take care of them first of all. And our final answer for this is a half x, cos of 2x minus 1. And a cos comes from the differentiation of a sine of exactly the same argument. When we differentiate the sine, it returns plus, so we need to maintain the plus that is already there. It produces times 2, so we need a quarter in front of it. We divide the half by another 2, plus c. Just checking the answers as well, just in case I'm writing stupid things up there. No, it seems to be okay. That's number 99, and the following 4 integrals are just very, very simple, all of them. Number 100, 4 bracket 3x minus 2 to the power of 3. We can of course cube the bracket, but it's much easier because it's linear, of the form ax plus b. Start with a higher bracket, 3x minus 2, higher power, add 1. And now adjust your constant at the front. This will produce a 4 times the 3 is a 12. 4 divided by the 12, so give us a third plus c. Nothing else to say. Number 101 and 102 are some that occasionally, when I give this particular book for practice to my own students, I do get some blank faces from year 13s when it comes to the next two, and it's shocking because they expect something very complicated and they have forgotten the basics. So let me just write the integral 101, and the integral of 101 is the square root of x square root of x dx. So the initial thoughts for something like this is, my God, this is not some kind of substitution, square roots of what is going on. The answer is, these are just indices. It's just square roots that we do in year 12. We should be able to do in year 12. It's just that at the moment we know way too many techniques and we might be thinking a little bit more complicated than we should. So first of all, this square root on the outside is something to the power of a half. So this is the square root here. And inside I've got an x, this is this x here, and I have another square root of x multiplying it. So I'm going to put times x to the power of a half. That's this square root here, dx. Simplify this, x to the 1 if you want, times x to the half. It will give you x to the power of 3 over 2. That is the interior of this bracket, but of course is now raised to the power of a half. Now a to the m or to the n, you multiply the powers. So this will now become x to the power of 3/4 dx. And this particular integration now, let me move that a little bit higher so we can continue writing there. Increase the power by 1, x to the 7/4, and then divide by the new power. 1 divided by that is of course 4/7 plus c. So this is integral number 101. And 102 is very similar, just a little bit uglier. We have 1 over x squared, and next to that x squared we got the cube root of x. The cube root of x dx is again more indices. Need to take our time to simplify. This is the denominator x squared. Cube root of x is of course x to the power of a third. Now we're going to use the rules of indices on the denominator still. So it's going to be 2 plus a third is x to the power of 7/3, okay, with a 1 still on the top, dx. What happens now from this particular line? We need to move it to the top for integration purposes. So we're going to write it as x to the power of minus 7/3 dx. I'm going to move out the way so you can see from this line to this line. So the x to the 7/3 has now become x to the power of minus 7/3. So now I can increase the power by 1. So if I increase by 1, it's going to go to the power of, what do we get in there? minus 4/3 there. Okay, so, and then I'm going to divide by the new power, so it's news at the front, and minus 3/4. My answer doesn't match in there. Have I miscopied or have I done something stupid? I'm out by a factor of 1/3, and I shouldn't be. We got x squared, cube root of x. The cube root of x, of course, power of 1/3. 2 1/3 is, of course, 6/3. Plus 1/3 is, of course, 7/3 to the power of minus 7/3. And if we increase the power by 1, I'm sorry, I'm not making it, unless that was meant to be an x squared in there, and I have actually missed it when I typed it out. I'm not quite sure. Okay, this, I cannot see anything wrong with what I'm doing in there, unless, as I said, I have there's a misprint in here, because the answer that I'm getting for this one should be minus 3/5. Unless, of course, I'm also doing something totally retarded, so I do apologize. I have this answer in there, and I just cannot, this clearly must have come from x to the power of minus 8/3, and that could have only have come if this was squared in there. But there's no square there. Maybe my printer didn't print it, maybe there's a typing error there, who knows? It doesn't matter. Okay, so we're going to go to the very last one, number 103. The integral of 3 over square root 2 minus 4x inside the square root dx. How are we going to do this one? Because we see square roots there, we might be tempted for a substitution. It will work. Substitution u is equal to that, or use the whole square root. But remember, this is linear. There's no x's on the top or anything like that. So if we write it on the top, there's your 3, and this bracket you can write it as 2 minus 4x to the power of negative half dx. Then we can finish it off because we can increase the power of the bracket by 1, 2 minus 4x to the power of a half. Now when we differentiate that, we're going to get a half from the power times a negative 4 from the differentiation of minus 4x, a total of negative 2. So we need to divide now whatever we got at the front with negative 2. So minus 3 over 2 bracket to the power of a half plus c, which of course is the answer that I got up there. Okay, so we're through with the number 92 to 103. Look at this 102. Maybe I'm doing something stupid. It doesn't really matter. So I will be seeing you very, very soon. And who's laughing now? I hope we all are. See you later. Bye.